All right, good evening. We have to discuss electrochemistry today, right? So we'll start it. So electrochemistry has mainly two parts. Mainly two parts. There is another one small part also. The first main part is electrochemical cells, right? So that is the major part in which the question is tested. And second one is electrolysis, and finally there is a small part on conductivity. Okay, so we'll start with electrochemical cells today, right? And then we'll move on. Okay, right. So before going into electrochemical cells, we have something called electrodes. Now, what do you mean by electrode is we have to go into it, right? So before starting electrochemical cells, we should know about electrodes. Now, what is it? Why do we need to know about these electrodes? What is the reason? So the main thing is one electrochemical is made up of two electrodes, right? So before going into electrodes, before going into electrochemical cells, we have to study about electrodes. Okay, right. So we'll speak about electrodes. Now, if you put a metal rod inside a aqueous solution, you will see some observations. Now, assume I am dipping a magnesium rod. I am dipping a magnesium rod inside a magnesium 2 plus solution, right? So this is the magnesium rod, and this is the magnesium 2 plus solution. Now if I dip it, what will happen is, no, I'll erase this, right. Now what will happen is, the magnesium particles, right, there are solid particles, right, so that magnesium particles will be releasing electrons, right, it will be releasing electrons and it will be removed as magnesium 2 plus, right. What will happen is the magnesium particles, right, it will be releasing electrons, right, and it will be forming magnesium 2 plus ions, right. So this is the thing that will be happening. Okay, so this is aqueous and solid. So then what will happen is these electrons, right, these released electrons will be left behind the magnesium solid, right, this will be left here because electrons can't swim, right, electrons are unable to swim, therefore they will be remaining in this solid, magnesium solid, and this magnesium 2 plus will be released into the solution, right. So magnesium 2 plus will be released into the solution. Okay, so magnesium, lot of magnesium 2 plus particles will be there, and this magnesium 2 plus particles will be also be there closer to the magnesium rod. Now this is the magnesium rod and this is the magnesium 2 plus solution. So the released magnesium 2 plus will be closer to this magnesium solid. The reason is now electrons are left behind this magnesium solid, and you all know that electrons are negative charges and magnesium 2 plus is a positive charge. So what will happen when negative and positive charge are closer to each other? They will attract, right? So due to this attraction force, what will happen is these magnesium 2 plus particles will be closer to the magnesium rod, right? So actually what will be happening is there will be a negative charge generating on the magnesium rod, right, and there will be a positive charge generating in the solution, right. So here it will be having a negative charge. The reason is due to the accumulation of electrons, it will be having a negative charge, and also the solution will have a positive charge due to accumulation of magnesium 2 plus ions, right. So what will happen is, so magnesium 2 plus will be closer, right. So this will keep on happening, so magnesium 2 plus will be keep on forming and it will be uh, keep on forming and it will be waiting closer to the magnesium rod. So at one point what will happen is the magnesium 2 plus ions which are closer to the magnesium rod, right, will quickly accept the electrons on the magnesium rod, right. It will be quickly accepting the electrons and magnesium rod, right, and it will be forming magnesium solid again, right. Initially what will happen, this will be happening. So when enough magnesium 2 plus are formed in the solution, it will be again reclaiming the electrons and forming the magnesium solid. So after some time what we'll see is you will see a equilibrium formed, you will see equilibrium form, right. So that equilibrium reaction is normally written as magnesium 2 plus plus 2 electrons and forming magnesium solid. Now what will happen is the speed of formation of magnesium and the speed of formation of magnesium 2 plus will be equal at a certain instance, and when that instance is happened, right, we say that there will be a dynamic equilibrium happening between magnesium and magnesium 2 plus, right. So let me brief it again. What will happen, you are dipping a magnesium solid into a magnesium 2 plus solution, and what will happen initially is this magnesium solid will be releasing electrons and forming magnesium 2 plus ions, and these electrons will be remaining in this magnesium rod, but the magnesium 2 plus ions will be released into the solution. Now these magnesium 2 plus ions will be still attracted to the magnesium rod. The reason is the rod has a negative charge and magnesium 2 plus has a positive charge, right? So electrons are negative charges and magnesium 2 plus are positive charges. So when this happens continuously, what will happen when this first reaction happens, that is the formation of magnesium 2 plus happens continuously, the concentration of magnesium 2 plus starts to build up in the solution, right. So when enough concentration is formed in the solution, right, concentration of magnesium 2 plus, what will happen is this magnesium 2 plus will be so much closer to the magnesium rod such that it will reclaim the electron on the magnesium rod and form the magnesium solid, right. So when the concentration is high enough, it will be again forming the magnesium solid, right. So there will be a situation where this both reaction speeds will be equal, right. So that situation is known as the equilibrium situation. When this equilibrium situation is achieved in such a system, we call it as an electrode, right. We call it as an electrode, right. So when this equilibrium is reached, right, when this equilibrium is reached, we say this type of a system as an electrode, right. Okay, so then this is the definition of electrode. So when scientists compare different metals, for example, now magnesium, this experiment was conducted with magnesium, right? And assume that they are around roughly, right? So I'll just give not the exact value. For example, I'll give around 10 electrons are present in the magnesium rod at equilibrium, right? Scientists have found out that around 10 moles of electrons are present in the magnesium rod, right. This is just a rough value given by myself, right, just for the understanding, not the exact values. Now then scientists, what they did was they dipped a copper rod, right, they dipped a copper rod inside a copper 2 plus solution, right. This is a copper 2 plus solution and this is a copper rod. So what will happen, same thing will be happening, right. Copper rod will be going to the solution as copper 2 plus, right. And also when the concentration of copper 2 plus is high enough to reclaim it, it will be again forming copper. So copper 2 plus will be again start to form copper. So this is same thing will be happening, right. So then it will reach equilibrium, copper 2 plus plus 2 electron is known as copper solid, right. So same thing that was done for magnesium was done for copper also. Then scientists, what they noticed was that the number of electrons in copper was less than magnesium. They noticed that, right. It's assumed there was 5 moles of electrons, here there was 10 moles of electrons, for example, right. So then when they took different metals and when they formed the electrode, they noticed that different electrode has different number of electrons at equilibrium. Different electrodes had different number of electrons in their equilibrium state, right. So what scientists did was they wanted to provide a numerical value for it, right. Now for example, now how do you classify class toppers and the like middle average students, how do you classify them, by looking at the marks, right. If a student scores are above 90%, we say that as a topper student. If a student scores around 60%, 60 50%, we say that is as an average student, right. So how do you classify this topper and average, based on their numerical scores, right, that based on their scores. So this is a numerical value. Same way scientists wanted to classify different metals, right, on the hierarchy by providing a numerical value, right. So they tried one thing, right. First they gave an attempt. What they did was, now you all can see, negative charges on the magnesium rod, right. So let me take the magnesium rod. So this was the first try of scientist, right. They dipped it, same thing. So magnesium rod has a negative charge, right? And solution has positive charge. At equilibrium they'll be having positive charge. So you can see a solution has a positive charge and the rod has a negative charge, right? So you can see there is a voltage difference, right? Now between plus and minus there is a voltage difference, right? So scientists, what they did was they tried to measure this voltage and provide a numerical value. What they did, they took a wire, right, and they connected one point of the wire to the rod, and they connected a voltmeter, right, and they tried the connect the next wire to the solution, right? So the difference between this negative potential and the positive potential will provide a value. They will provide a value, right? So then they try to use that value to build up a order, right? But there was a problem with it. What was it is, now connecting the wire to the metal rod was easier, right? So there was no issues with that. But the problem came when it was when was making a connection to the solution, right? So making a connection to the solution was a problem. What is the problem is, now you all know wire is also made up of metal, right? If you take current wires, mainly it is copper, right? So mainly copper wires are used, right? So always there is a metal inside a wire. So actually inside a wire there is a metal. So if I now let me zoom this place, the point where the wire is made connection with the solution. Now this is the wire, right? It is going right into the solution. Now actually wire is also metal, right? So what will happen is, actually you are dipping another metal inside the solution. So this fellow, right, the wire fellow, right, will also try to form an electrode, right? It will also try to form an electrode, because wire is a metal and you are dipping into a solution. So metal solution, that is electrode, right? So what will happen is, here also there will be a new electrode forming, right? So then you can't measure the actual voltage, right? So that was the problem faced by the scientist, right? So they tried to figure out another way to compare these values, like comparing the students. They wanted to compare it. So what they did was, right, now you can't, now they found out that we can't actually measure the actual voltage, but still we can compare with someone. Now let's assume, right, now they couldn't provide numerical values like this, right? So what they did was, they took an average fellow, right? They took an average electrode and they compared the other electrodes with them. Assume that like that. Now there is an average student, average student is 60%, right? Now there is one student scoring 90%, another student scoring 35%, right? Now actually there is no numerical values, right? So you can't compare them. That is, you can't actually measure the actual voltage, right? You can't measure the actual voltage. So they try to compare, right? Now let's assume, let me give an example, right? Now let's assume that in this period there is no measuring tape. Assume like that, right? So there is no measuring tape and there are three students. One fellow is like middle height, another one is tall, right, and another fellow is short. Now you wanted to measure the height, right, but actually you don't have a meter ruler or measuring tape to measure it, right? So you can't actually measure the height, right? You can't give the actual numerical values, but still you can compare, right? You can take this fellow as the reference fellow and you can tell that person 1, if I name this as person 1, person 1 is taller than the average person, and we can say person 2 is shorter than the average person. So even though you are not having a measuring tape to measure the actual values, but you can still compare them with another person, right? So that is what the scientists did next, right? They can't actually measure the actual voltage, right? So they wanted to compare it with another electrode. So the electrode that was used to compare is known as the standard hydrogen electrode, right? So the other electrode that was used to compare the electrode, right? So if you have no, if you want to compare magnesium electrode, you can't measure the actual voltage, but still you can compare with it with another person, right? So electrode that is used as a reference electrode, right, we call it the reference electrode, that is known as the hydrogen electrode, right? So all the electrode potentials were compared with the hydrogen electrode and they made a series of table, right? So it is a table, we call it as the electrochemical series. So that you all might have seen in the resource book also, electrochemical series, and they have given potential values, right? So those values are made in comparison with the standard hydrogen electrode. They are not the actual voltages, right? Okay, so before going into the comparison, let me show you a standard hydrogen electrode, right? So standard hydrogen electrode, you must know to draw the standard hydrogen electrode. They can ask in the questions, right? So you must know to draw it. So actually it is a structure like this, right? So and you have a platinum wire with the platinum solid, right? And then you are dipped it into a solution of H plus ions, right? So H plus ions, and this is here is where the H2 gas is pumped in, and this is the platinum wire, right? This is the platinum solid. Now we call it as the standard hydrogen electrode, or we'll call it as the SHE. We call it SHE or standard hydrogen electrode, right? Now why is it called as standard hydrogen electrode? Because this electrode is made at 1 atm pressure, right? 25 degrees Celsius temperature and 1 mole dm minus 3 concentration. So the standard conditions are used, therefore this is known as the standard hydrogen electrode. So the concentration of H plus is 1 mole dm minus 3, right? And the pressure of H2 gas that is pumped in is 1 atm, that is 1 into 10 to the power 5 pascal, right? We call it, we can give it in pascal or we can give it in atm also, right? So this is the structure of a hydrogen electrode, you must know to draw. Okay, wait. Right, now there are mainly two functions of this platinum, right? Now why do we use a platinum? There are two functions, right? Mainly there are two roles of platinum in this electrode. First one is it will provide an external connection to the another electrode. Now actually electrodes, two electrodes make up one electrochemical cell, is right? So you have to connect two electrodes. So to connect two electrodes there must be a connecting point, right? Each and every electrode must have a connecting point. So the connecting point is the platinum, right? So it will provide a place for the connection with the external electrode. That is the first use of this platinum. And second one is H2 gas. It is a gas, right? So H2 reaction with H plus is bit difficult, right? Because gases, like, they are moving in open areas, so the reaction is a bit difficult, right? So what platinum does is it will be acting as a catalyst, and it will be attracting the H2 gas into this platinum and make it dissolve, make it react with the H plus, right? Now you can see platinum is in contact with the H plus. So what will platinum do is it will attract the H2 plus, right? It will make it dissolve in the platinum and make it react with H plus ions, right? So those are the two functions of platinum. Some might have doubts, why do we have used platinums? So those are the two functions, right? Okay, right. Now all of the potential of electrodes were compared with this hydrogen electrode, right? And also scientists assumed that they made an assumption that the voltage of this hydrogen plus, now you can see all the electrodes will be building up electrons into their rod, right? So here also electrons will be building in the platinum solid. But scientists, what they did was they made an assumption that number of electrons that is formed in this hydrogen electrode, right? Number of electrons that is present in this hydrogen electrode is negligible. They made an assumption like that, right? And they said that this potential of this hydrogen electrode is 0 volt, right? No, this is not actually 0 volt. This is the assumption made, right? Now they are going to compare it, right? So they made assumption that number of electrons in the hydrogen electrode is negligible, and therefore the voltage of it is 0 volt. That is the assumption they made, right? Right, now let's see how are they comparing the other electrodes with the hydrogen electrode. Now actually this is what is happening. Now let me draw this a little bit closer. Right, okay, this is the hydrogen electrode. Now let's assume we want to compare another electrode. We'll compare magnesium electrode, we'll compare magnesium electrode. right? So what is a magnesium electrode? Magnesium, when magnesium rod is dipped in magnesium 2 plus solution, and when it reaches equilibrium, that is known as a magnesium electrode, right? Simple as that, right? Now, how do they compare it? First, they'll be connecting a voltmeter across the both electrodes, right? They'll be connecting a voltmeter. Now, voltmeter, and the other part will be connected to this platinum. So this is the use of platinum. It is used to connect with the external circuits, right? Okay. So then there will be another person involving to connect the two solutions, right? So to connect both the solutions, no, actually that is not connecting, right? So I'll tell the function of it later. So there will be a person known as the salt bridge. There is some fellow known as the salt bridge. So it is something like this. So that is present in between two solutions, right? Okay, so I'll tell the function of salt bridge later. Now this is a salt bridge. Salt bridge. Right. Now what will happen is here electrons will be there. Right. Now you know, right, at equilibrium electrons will be there in both the electrodes. Now let's assume magnesium has more electrodes than hydrogen. Now if for example I'll take there are 3 electrons in magnesium and 2 electrons in hydrogen, right? Let me take like that. Now what will happen is you can see magnesium will have a negative charge more than hydrogen, right? Because it is having more electrons. So this part will be more negative compared to this part, right? So actually, no, this is going to be more negative, right? So also we took, now you can see here the potential, the voltmeter reading will be the difference between these two potentials, right? The difference, it is going to be the difference. Now actually it will be reading the difference, that is the actual scenario, but we are taking assumption that hydrogen electrode is giving 0 volt, right? We have to make assumption that hydrogen voltage of hydrogen electrode is 0 volt. Therefore the reading of this voltmeter will directly give the electrode of magnesium, because this is 0 volt, right? So difference is actually the value of magnesium. Understood? Now if let's assume like this. Now you are accelerating from 0 to 100. Let's assume you are moving in a vehicle and you are accelerating from 0 to 100. Right? Now what is the difference in speed? The difference is 100 minus 0. That is 100, right? So the difference is 100. If one value is 0, the final speed is also going to be 100. Right? If one value is 0, the difference is going to be equal to the final speed. Understood? Same way, 1 is 0, this value is 0, so difference is going to be the voltage of this magnesium electrode. Understood? So something like that, similar like that. Okay. So actually this will be reading the voltage of magnesium compared to hydrogen, not the actual voltage. We can't measure the actual voltage, right? Now if it forms more electrons than these, right, this reading will be a negative reading. That means the potential will be given in negative values. If the number of electrodes formed in magnesium is higher than the number of electrons formed in hydrogen, then this reading will be a negative reading, right? So magnesium will be forming however more electrons. If you use copper, now if you use copper here, the electrons formed on the copper will be lesser than hydrogen. Now this, if I take this copper, so in copper the number of electron is different, right? So actually the electrons formed on copper metal will be lesser than hydrogen. So then this reading will be a positive value, right? Like that, right? So if electrode gives more electrons than hydrogen, the potential is going to be a negative value, and if an electrode provides lesser electrons than hydrogen, the reading is going to be a positive value, right? So like that they measured, they connected different electrodes to the hydrogen electrode, and they measured the voltages, and they prepared a series, and that series is known as electrochemical series, right? So if you all have the resource book, I think it will be on page number, wait, page number 249, right? So this is my old resource book, so it has in page number 249. This is a series giving the reduction potentials, right? So the negative fellows means they are having more electrons compared to hydrogen. If they are having positive potentials, mean they are having less electrons compared to hydrogen, right? So this is how they measured the voltages of electrodes comparing with the hydrogen electrode, and they made a series, right? So that is known as the electrochemical series, right? Then, so that is the electrode idea and everything understood, okay? The next thing is we have four main types of electrodes. We have four main types of electrodes. The first one is known as the metal ion electrode. Metal ion electrode. So wait a minute. Right. The first type of electrode is, so mainly I having four types of electrodes. The first type is metal ion electrode. Now what do you mean by this? Metal ion electrode. So that means if a metal is in connection with its metal ion, now let's assume magnesium in connection with magnesium 2 plus ions, and it forms a equilibrium, right? So actually electrodes form equilibriums, right? So if it forms equilibrium like this, we call it as a metal ion electrode. Understood? So magnesium electrode, copper electrode, zinc electrode, those are examples, right? And the second type is metal insoluble salt electrodes. Metal insoluble salt electrodes. Now you can, by looking at the name itself, you can tell. If a metal is in contact with its insoluble salt, we say that type of an electrode as metal insoluble salt electrodes. So we have two examples for that. The first one is calomel electrode. So there is something called calomel electrode. Calomel electrode. And you must know to draw this electrode itself, right? Because they can ask in exam calomel electrode, so you must know to draw it, right? So let me draw it. So it will be looking like a mug, right? Like a jar it will be looking like. So if I draw it, right, something like this, okay? So you'll be having a mercury here. You'll be having mercury at the bottom. Above that there will be Hg2Cl2, right? And then above that you will be have a solution, and there will be a platinum electrode, platinum solid metal wire, right? Okay. So the bottom part will be mercury liquid, and the just above that you will have Hg2Cl2, which is an insoluble salt of mercury, right? And here you will be having saturated KCl solution, not just say KCl, it is a saturated KCl. You have to remember that, not just KCl, it is a saturated KCl solution. You have to remember that, right? And then here you go the platinum wire, right? So this is the platinum wire, and this is used to connect with the other electrodes, right? Okay. And then we call this as the separator. There is something called separator, so no need to know the function about it, right? So just if you all know to draw the structure, that's enough. So check your resource books and try to draw the exact diagram, and here only the external connection is made, okay? Right. So the next thing is, this is one example for metal insoluble salt electrode, that is calomel electrode. And the second one is silver chloride electrode. We have silver chloride electrode. So you can see here, come to my calomel, you can see metal insoluble salt. Metal, mercury liquid is the metal, insoluble salt is Hg2Cl2. So metal insoluble salt electrode. The second one is silver chloride. By looking at this itself, we can tell silver is the metal, silver chloride is the insoluble salt. So this comes under metal insoluble salt, right? So this is like a bullet, right? You know, have you seen bullets? So it will be just having a structure like a bullet. So you all must know to draw this, okay? right? So you have a silver wire, and the silver wire some part is coated with silver chloride, AgCl, silver, and the solution has saturated KCl solution, right? So saturated KCl solution, and then this part is known as the ceramic quartz, right? So the deep part, right? So look at your resource books and learn to draw the exact diagram, okay? Right. So this is metal insoluble salt. Metal is silver, insoluble salt is silver chloride. Okay. Then the next thing you must know is to write the electrode equilibrium reaction. Right. Now you can see magnesium, magnesium 2 plus. What is the equilibrium formed? Magnesium 2 plus 2 electron will be forming the magnesium solid. This is the equilibrium reaction for magnesium electrode, right? But some can write in this way also, right? Magnesium is in equilibrium with magnesium 2 plus electrons. Like this also you can write the equilibrium reaction, right? Because you can write it in either ways because this equilibrium, right? So but there is a issue. There's So this is also correct, right? The second method is also correct, that is writing it as like a oxidation reaction also correct, but the IUPAC, right, has given a rule to follow, right? What is the rule is you have to always write the equilibrium reactions as a reduction reaction. You have to always write them as a reduction reaction. That is a rule that everyone must follow, right? So if you write like this in your exams, 0 marks, right? So always equilibrium reaction must be written as an reduction reaction, right? Okay. So silver chloride, how can you write the equilibrium reaction? Now who are the species undergoing oxidation and reduction? Now if you take electrode, the same species, right, the same species will be going oxidation as well as the reduction. You can see magnesium 2 plus is reducing to magnesium, all the same way magnesium is oxidizing to magnesium 2 plus. So the same element is undergoing oxidation and reduction, the same species, right? So you can see magnesium 2 plus and magnesium 2 plus is reducing, magnesium is oxidizing. So we say this type of a reaction as redox couple, right? We call them as redox couple. So always there is a couple here, and same species will be undergoing oxidation and reduction. That is a characteristic of electrodes, right? So electrodes have a special characteristic, that is they have a couple. The same species will be oxidizing as well as reducing. Now you can see magnesium and magnesium 2 plus. Same way, if you take in here, you can see the couples are silver and silver chloride. So yeah, how do you write it? Now you can see in silver chloride the oxidation number of silver is +1 and silver oxidation number is 0, right? So reduction is going from +1 to 0, that is known as reduction, right? So you have to write in reduction form. So AgCl, that is where silver has +1 oxidation number, and if it takes an electron it will be going to silver, right? So when writing reactions, physical states are must, okay? Physical states are must, right? Now this is the reaction. You had to balance chlorine, so what you have to put, you have to put a Cl minus aqueous here, right? So how do you balance, how do you write the equilibrium reaction for calomel? Now you can see, let me erase this. Right, no need to erase, I think. Yes, let it be like this, right? So calomel, how do you write it? Example, calomel. Now who are the redox couple? Hg and Hg2Cl2, right? So in Hg2Cl2 the oxidation number of mercury is +2 +1, I mean +1, and Hg liquid is 0, right? So +1 to 0 is the reduction way. That is how the reduction happens, right? So Hg2Cl2, so same way as reducing redox reaction, you have to write it here, right? Same way, how do you balance it? Same way you have to balance it here. So Hg2Cl2 is going to Hg liquid, right? You can see here the oxidation number is, first I had to balance the mercury, 2 mercury I had to put. So here the oxidation number is +2. In Hg2Cl2 the oxidation number is +2, and here oxidation number is 0, so it is reducing by taking 2 electrons, right? So you have to balance chlorine, so here there are 2 chlorine, so you have to put 2 Cl minus equals, right? I hope you all understood the way to balance it, okay? And physical state is a must, right? So liquid, solid, you have to put it, right? So this is the second type of electrode. What is it? Silver, silver chloride. And the third type of electrode is gas electrodes. We have something called gas electrodes. That is the third type of electrodes, right? Third type is gas electrodes. So you have two electrodes. One is the standard hydrogen electrode, that is one example, and another one is you have chlorine electrode. Chlorine electrode is another example for gas electrodes, right? Okay. And then you have oxygen electrodes also. So all these three have the same structure, same like the hydrogen electrode, only all of them has. Okay, so I'll draw it one. So here if it is a hydrogen electrode, hydrogen gas will be pumped, right? So here same, these all are same platinum. If it is a hydrogen electrode, H2 gas will be pumped from here, H plus solution will be there. If it is a chlorine electrode, Cl2 gas will be pumped from here and Cl minus solution aqueous will be present in the solution. If it is oxygen electrode, oxygen gas will be pumped here and OH minus will be there in the solution, right? If it is a oxygen, it will be OH minus will be there and O2 will be pumped. If it is a chlorine, Cl2 will be pumped and Cl minus will be there in the solution, right? So you have three examples for gas electrodes: standard hydrogen electrode, chlorine electrode and oxygen electrode, right? Now we use standard hydrogen electrode to compare with the other electrodes, right? We use them as a reference electrode. There are two other electrodes that can be used as a reference electrode that can be used, right? So first one is the calomel electrode and the second one is silver silver chloride electrodes. So these two electrodes also can be used as a reference electrodes. The reason is their potential does not change during the experiment time, right? So if you are comparing with another electrode, during that time period their potentials remain constant, right? Their potentials remain constant, therefore these two electrodes also can be used as reference electrodes, okay? And the last and the final electrode is the redox electrode. The final type of electrode is the redox electrode, right? Redox. So there is one example, Fe2 plus Fe3 plus electrodes. I forgot to write the equilibrium reaction. Now how do you write the equilibrium reaction for hydrogen electrode? If it is a hydrogen electrode, you will be having H2 gas pumped from here and H plus solution in the H plus will be there in the solution. Now, right? So who is the redox couple? Hydrogen and H plus, right? So who is reducing? H plus is reducing to H2, right? That is what is happening. So how do you write? H plus is reducing to H2, right? So first you have to balance H plus. You can see 2H here. So the oxidation number is plus 2. It is reducing to 0. So how it reduce? It is taking 2 electrons and reducing to H2, right? Same way, how to balance the chlorine electrode? So there is only two differences. First is here chlorine gas will be there and in the solution Cl minus will be there, right? So now who is reducing to who? Is chlorine reducing to Cl minus or Cl minus reducing to chlorine? Now oxidation number of Cl minus is -1, oxidation number of chlorine is 0, right? So Cl2 is reducing to Cl minus. So to balance, first you have to balance chlorine, right? So you can see oxidation number is 0, here it's -2, right? So actually it has reduced by taking 2 electrons, right? So physical states is a must, okay? Chlorine gas 2 Cl minus. So finally, how do you balance O2? Oxygen gas OH minus, right? So here you can see oxidation number of oxygen is 0, here oxidation number of oxygen is -2. So 0 to -2, so oxygen is reducing to OH minus, right? So I had to put 2 here. So then here 0, here it is going to be -4, right? So it is taking 4 electrons and forming this. uh, and to balance hydrogen, what I had to put, I had to put 2H plus here. I think now it's balanced. 2 hydrogen, overall charge is also minus 2, and everything is balanced, right? Okay. So this is same as balancing the redox reactions, right? First, you have to find the number of electrons that is transferred, and then you have to balance oxygen, and finally hydrogen. That is the order, right? And next type of electrode is redox electrodes, right? So redox electrodes means the solution contains both the redox couple. So example we have is Fe2 plus Fe3 plus electrode, Fe2 plus Fe3 plus electrode, right? So it is a simply a beaker having a platinum solid, right? And the solution contains Fe2 plus and Fe3 plus, right? uh, so how do you write the reaction? Who is reducing to who? Fe3 plus is reducing to Fe2 plus, right? So Fe3 plus aqueous plus electron reducing to Fe2 plus aqueous, right? So remember, always equilibrium reactions are written as reduction reactions. Okay, so those are the four types of electrodes: metal metal ion, metal insoluble salt, gas electrodes, and finally redox electrodes, right? So next, final part of electrodes is the IUPAC naming for electrodes, right? So how do you name electrodes? That is the last part we have, right? So there's a simple rule to follow. Wait. So I'll erase this part. So in naming IUPAC electrodes, there is a simple rule. First one is, normally a name consists of what? A name consists of first name, middle name, last name. Those are the three parts of a name, right? Okay, so normally electrodes also has first name, middle name, and last name, right? So the first name, right? We usually write the name of the connector metal, right? We usually write the name of the connector metal. And in the last name, right, we usually write the ion in the solution, right? First name the connector metal, last name we usually write the ion in the solution. The ion which is present in the solution is written as the last name. So in the middle name the rest is written, right? So rest is written in the middle name. So when we are doing the examples you will understand it. So that is the first rule. And second rule, if the ion in the solution, if ion in the solution if ion in the solution right, if ion in the solution is present in redox couple, you know the redox couple, right? Here hydrogen and H plus, in this case chlorine and Cl minus, in this case O2 and OH minus, here Hg and Hg2Cl2, here Ag and AgCl. So those are the redox couple. If you take redox electrodes, Fe2 plus and Fe3 plus, those are the redox couple, right? So if ion in the solution is present in redox couple, you have to mention the concentration of it, right? Concentration must be mentioned, right? Concentration must be mentioned. And also, if another species, if there's a gas, right, and if that gas is present in the redox couple, you have to mention the pressure also. So when you are doing examples we'll understand, right? Concentration must be mentioned and pressure also must be mentioned. That is the second rule. So the third rule is, when you are separating physical states, right? So if there is a combination of aqueous and aqueous, if there are two aqueous solutions close to each other, you have to simply put a comma to separate them. A comma is used, right? That is the first law. If there are two aqueous solutions, we use a comma to separate both of them. If there are any other combinations like uh, any, and for other combinations, right, we had to use simply a straight line, right? Simply a straight line is used. If you want to separate, let's assume solid and gases, you have to put a comma. If you want to separate solid and solid, if you want to separate aqueous and gases, you have to put a straight line, right? So if only for aqueous and aqueous you have to put a comma, and for any other combinations you have to use a straight line to separate the phases, right? That is the third law. And the fourth law is, if there are many species present in the solution, um, right, the fourth law is, if there are many species present in the solution, the one with the lower oxidation number is written first, right? If there are many species, there are many species, the one with low oxidation number is written first. So these are the main rules. So when we are doing examples, you will understand it, right? Okay, so these are the main rules to name a electrode using the IUPAC, right? Okay, so first example, we'll name a magnesium electrode simply. So magnesium electrode has magnesium and the magnesium 2 plus solution. Magnesium 2 plus magnesium. Right. Right. First name. Oh, before that, let me write the redox equilibrium reaction. So the redox couple are magnesium and magnesium 2 plus, right? So actually magnesium 2 plus is reducing to magnesium. Write the physical states when you're writing, right? So solid, aqueous. So what is the first name? Connector metal. So who is connecting the with the external electrode? Magnesium solid is gonna react. Magnesium solid is gonna be connected, right? Because when if you are connecting a wire from magnesium only, you will connect another electrode or voltmeter or something. You will connect it. So magnesium is the one who is providing an external connection from the electrode, right? So first name is the connector metal, that is in here. It is magnesium solid, right? Magnesium solid. Last name is the ion in the solution, all right? So what is the ion in the solution? Magnesium 2 plus, that is comes as a last name. So the remaining, if there are remaining ions present, if there are remaining species present, right, so that will be coming as a middle name. But you can see in magnesium electrode only magnesium and magnesium 2 plus are present. Is there any other species to name? No, right? So there is no middle name in this electrode, right? Okay, the first rule is done. If ion in the solution is present in redox couple, concentration must be mentioned. Now what is the ion here? Magnesium 2 plus. Is it present in the redox couple? Yes, it is present in the redox couple. Then the concentration must be mentioned. So normally the concentration is 1 mole dm minus 3, because these are done at standard conditions, right? So if it is standard condition, the concentration is 1 mole dm minus 3, right? And also pressure also must be mentioned, right? So pressure is mentioned only for gases. If there are gas species present, we mention the pressure. So here there is no gas species, therefore pressure is not to be mentioned, right? And the third rule is, if there is aqueous and aqueous, you have to put a comma, and for other combination you have to put a straight line. So now here you can see solid and aqueous are present, right? So if you want to put solid and aqueous, it is not aqueous and aqueous, right? So there is no comma. And for other combinations you have to put simply a straight line. You can put a slash also, so better to put the straight line. Those are the three rules. Right. So fourth one is, if there are many species, the one with low oxidation number is written first. So here only two species are there, therefore this is the final IUPAC name, right? So magnesium solid, straight line, magnesium 2 plus aqueous, 1 mole dm minus 3, right? So that is the first example, right? Second one, I'll erase this. So I am not erasing this because I have to write the IUPAC name, so I am keeping it, right? Next one is how do you write the IUPAC name for hydrogen electrode? So I'll draw the hydrogen electrode. That is a simple one, right? H plus H2, right? And you have a platinum. What is the first name? Connector metal, right? Who is connecting with the external circuit? Platinum, right? Platinum is the one who is connecting with the external circuit. So here only it will provide external connection. So platinum is the first name. Platinum is the first name. And physical states must be mentioned solid. What is the last name? Ion in the solution. Who is the ion in the solution? H plus, right? So H plus is going to be the last name. That is the ion in the solution. H plus aqueous. So is there a middle name? Yes. You can see platinum H plus H2. Three species are present. So who is the middle name? H2 is the middle name. Alright. So let me keep some space. H plus aqueous. Here it's gas. Right. First rule is done. Second rule. If iron in solution is present, if iron in the solution is present in redox couple, concentration must be mentioned. So who is the iron in the solution? H plus. Is it present in the redox couple? If you write the equilibrium reaction, you can see 2H plus aqueous plus 2 electrons is in equilibrium with H2 gas. This is the equilibrium. Now you can see H plus is in the equilibrium, right? You can see this is a redox couple. Who are the redox couple? H2 and H plus. So H plus is in the redox couple. So therefore concentration must be mentioned. What is the concentration? This is a standard hydrogen electrode. That means 1 mole Dm minus 3. Right? Okay. And pressure also. So if there is a gas present, you must mention the pressure also. So is there a gas present? Yes. So you must mention the pressure. So the standard pressure is 1 atm, right? So I mentioned earlier, at standard conditions the pressure is 1 atm. So you have to mention like this, right? Third one, if aqueous and aqueous are present, you have to put a comma. For other combination, you have to put a straight line, right? You can see solid and gas, so that will be straight line. You have to put a straight line. You can see gas and aqueous, you can put a straight line there, right? And if there are many species, the one with low oxidation number is written first. So here is there is no issue. So the rule 4 comes rarely in the questions, right? That means if there are many species, right? If for middle name there are many species for the middle name, then you have a confusion who to write first. Then only the one with the low oxidation number is written, right? So here in the middle name only one is present, so therefore there is no issues, right? So this is the um, electrode notation for hydrogen electrode, right? Okay. So oxygen electrode, chlorine electrode, those are same way, right? So it has the same structure, right? So chlorine means Cl2, Cl minus. O2 oxygen electrode means O2, OH minus, right? Okay. So I didn't do for that. Right. Next one is the how do you name for calomel electrodes? Look at that. Let's look at that. Right. So caramel electrode, I have the picture here, right? Now who are the species present? Platinum, KCl, Hg2Cl2, Hg, right? So you can see there are a lot of species present, right? So what is the first name? Connector metal. Now who is connecting with the external circuit? Platinum, right? You can see platinum is the wire that is extending, so that only will connect with the external circuit, right? So you have to write platinum first. Platinum solid, huh? Right. What is the last name? Ion in the solution. Who is the ion in the solution? Now KCl, if you take, KCl is ionic compound, right? So KCl will be completely decomposing. It means completely ionizing and forming K plus and Cl minus, right? So actually the solution will have K plus and Cl minus, not KCl, right? So then these are the ions present in the solution, K plus and Cl minus, right? So when writing, we ignore this K plus, right? We do not write the concentration of K plus because you can write it, right? You can write it as K plus and Cl minus for the last name, but normally we write only Cl minus aqueous, right? So in these situations, write only Cl minus, no need to write K plus because that is spectate ion, right? So therefore no need. Actually the importance is you have to put Cl minus is the aim, right? So you can't just put Cl minus, you are putting KCl, right? So no need to mention K plus, only Cl minus is enough. That is a one exception, like something like exceptions only, right? So the ion there are two ions in the solution, K plus and Cl minus. Now KCl be ionizing, right? So the K plus and Cl minus will be present. We do not write K plus, we write only Cl minus, right? So Cl minus is the last name. Alright. So for middle name, you have Hg and Hg2Cl2. Two are present. Two species are present for the middle name. Hg and Hg2Cl2. So who are you gonna write first? There comes the fourth rule. Right. Before that, let me go in the order. First name written, middle name is the one that must be written, last name is the ion in the solution, that is also written. So middle name, there are two species, Hg2Cl2 and Hg. So if there are many species, the one with low oxidation number is written first. So you can see Hg2Cl2, what is the oxidation number? Plus 2, right? Hg 0. So who is having a low oxidation number? Hg, right? So Hg must be written first and then Hg2Cl2. So see, when you are having many species only, you need this fourth rule, right? So first one is done. If ion in the solution is present in redox couple, concentration must be mentioned. So who is the ion in the solution? Cl minus is the ion in the solution. Is it present in the redox couple? Look at the reaction. Cl minus is present in the reaction. Is it present as a redox couple? Who are the redox couple? Hg2 plus and Hg2 plus and Hg. Actually, those are the redox couple. You see, now you can see chlorine's oxidation number is not changed, right? In Hg2Cl2 also the oxidation number is -1. In Cl minus also oxidation number is -1. So Cl minus has not taken part in the reaction. It is just present in the reaction. It is not taken part, right? So it is not the oxidation reduction couple. Who are the oxidation reduction couple? Hg and Hg2Cl2. Those are the two oxidation redox couple, right? Hg and Hg2Cl2 are the redox couple because those are the ones who are oxidizing and reducing. Cl minus is not oxidizing or not reducing, right? It does not involve in both the things. So Cl minus is not in the redox couple, so no need to mention the concentration. And there is no gases, therefore pressure is also no need to be mentioned. Third one is to separate aqueous comma must be put. For any other combination, straight line must be put, right? So you are having solid and liquid, so straight line, liquid and solid, straight line, solid and aqueous, straight line. So this is the IUPAC name for calomel electrode, right? So if you are having confusions with this one, now see Cl minus is not involving in oxidation or reduction, it is just present, right? See in Hg2Cl2 also the oxidation number of chlorine is -1. In the product side Cl minus is present, that also has the oxidation number -1. So it has neither oxidized nor reduced, right? So this is not taking part in the redox couple. So no need to mention the concentration. Alright. Then the IUPAC name for silver chloride. First name is the connector metal. So in silver chloride, who is connecting with the external circuit? Silver. Silver is the one that is connecting with the external circuit. So silver solid is the first name. Last name is the ion in the solution. Who is the ion in the solution? So here also you have saturated KCl, right? So ions are K plus and Cl minus. We do not write K plus, only Cl minus is written. So Cl minus aqueous. So who are the middle names? You have only AgCl remaining, so AgCl is the middle name, right? So only AgCl is remaining, so AgCl is the middle name. If ion in the solution is present in redox couple, concentration must be mentioned. So Cl minus, is it present in the redox couple? See, in AgCl also the oxidation number is -1. In Cl minus also oxidation number is -1 when you look at the reaction. So you can see it has neither oxidized or reduced, right? Also the redox couple is silver chloride and silver, not Cl, right? Silver chloride, that is actually silver plus, and silver is the original species, but when they are asking redox couple, you have to mention silver chloride and silver, right? So Cl minus is not in the redox couple, so therefore no need to mention the concentration, and there is no gases present also, so pressure is also no need to be mentioned, right? And the third one, to separate the physical states, you can see solid, so straight line, solid aqueous, straight line. And finally, if there are many species, right? So here only in the middle name only one species is present, so rule 4 is not applicable for this situation, right? The final electrode remaining is Fe2 plus Fe3 plus, right? Let me draw that also. That is the redox electrode, right? Redox electrode Fe2 plus Fe3 plus. You have a platinum, huge platinum, and in the solution you have Fe2 plus and Fe3 plus, right? Right, who is the connector metal? Platinum, right? Platinum is the one who provides the external connection to the circuit. So platinum solid is the first name, last name is the ion in the solution. Now there are two ions in the solution, right? So who are you going to write first? The lower oxidation number is written first. Who is having lower oxidation number? Fe2 plus, right? So Fe2 plus is written first and then followed by Fe3 plus. Do you have a middle name? No, right? So only three species are present. So first name and the last name are present. Last name also, the lower oxidation number is written first, right? So if the ion in the solution is present in the redox couple, you have to mention the concentration. Are these present in the redox couple? Yes, right? If you write the reaction, you can see Fe2 plus will be going to Fe3 plus and Fe3 plus will be reducing to Fe2 plus. So redox couple both are present. Therefore concentration must be mentioned. That is 1 mole Dm minus 3. Fe3 plus also aqueous 1 mole Dm minus 3. Right. So there is no gases present, therefore no need to mention the pressure, right? So third one, to separate the physical state, solid and aqueous, you are separating it by straight line, and then you have aqueous aqueous. How do you separate aqueous aqueous? By a comma, right? So you have to put a comma between Fe2 plus and Fe3 plus. And the fourth rule we already applied. So this is the IUPAC notation for redox electrode Fe2 plus Fe3 plus, right? Okay, right, and the final part in electrodes, that is the factors affecting electrode potential. Factors affecting electrode potential. Now we know that electrochemical series, you all have seen it, right? So that electrode chemical series, there are certain potentials, right? Now those potentials can be changed by changing certain factors. By changing certain factors, those potentials can be changed, right? So what are those factors? That is what we are going to look at it, right? So the first factor that will affect the redox potential is temperature, right? The first factor that will affect the redox potential is temperature. If you change the temperature, the reduction potential, we call that voltage. So when you are measuring a voltage compared to hydrogen electrode, right, that voltage is known as the reduction potential, right? So that reduction potential changes when you change the temperature. How? Let's assume one electrode, magnesium electrode, right? So I'll take magnesium electrode as an example. So these are not described in the resource book, they have just given all the factors only, right? So I'm telling this like to understand because it makes sense, right? So you can make sense with that. So there can be questions also, right? What is the equilibrium reaction? Magnesium 2 plus aqueous plus 2 electron equilibrium with magnesium solid, right? This is the equilibrium reaction, right? Let's assume delta H is positive in the forward reaction. Delta H is positive. No, actually in redox what is happening? In electrode what is happening? Electrons are present in this magnesium solid, right? Therefore, it is having a negative charges inside this magnesium solid electrode. Let me draw a little bit bigger. So this magnesium solid electrodes are present, right? So that is only what determines the potential of it, right? Okay. Now let's assume I am increasing the temperature. I am increasing the temperature. Right. Last class we discussed KP/Kc. So according to Chatelier's principle, if you increase the temperature, system will try to decrease it. To decrease it, it will favor the endothermic direction. So the forward reaction is endothermic here. So if you increase the temperature, system will favor the endothermic direction. So if it favors the endothermic direction, the electrons amount will be reducing, right? So you can see electron sign the reactant side, so electron number will be reducing. If the electron number reduces, what will happen? The number of electrons on this magnesium solid will be decreasing, right? As a result, what will happen? Reduction potential will be increasing. Reduction potential will be increasing, right? So when you change the temperature, potential increases. That is the first factor which will affect the reduction potential of electrodes. And the second factor is concentration of electrolyte. Now, what is the electrolyte? I write concentration of electrolyte. Now, what is this electrolyte? Electrolyte is the aqueous solution, right? Now, same thing. Magnesium 2 plus 2 electron. Now, I am changing the concentration of electrolyte. What will happen? So, if I increase the concentration of magnesium 2 that is electrolyte, right? If I increase it, system doesn't like it. System will try to decrease it, right? System will try to decrease it. Therefore, it will try to favor the reaction which decreases the magnesium 2 concentration. So to decrease it, it must favor the forward reaction. Then the electrons number will be decreasing. Then the reduction potential will increase, right? Because reduction potential, the more electrons present, the more negative the reduction potential. If lesser electrons, then more positive. So electrons reducing, reduction potential will increase. So by changing the concentration of electrolyte also, you can change the reduction potential. By changing the temperature also, you can change it. Those are the first two factors. And the third factor is the nature of the electrolyte, right? Third factor is the nature of the electrolyte. So nature means, like, will it dissociate completely or partially? That is what is known as nature. Nature of the electrolyte. So if we change the nature of electrolyte, so I don't want to explain this deeply, just have the idea. Nature of the electrolytes also affect it, right? So nature of the electrolyte means how well the solid dissociates, how well the ionic compound ionizes in the solution is known as the nature. So if it is a good ionic compound, the more magnesium 2 will be provided. As a result, reduction potential can be changed, right? So no need to have a big idea about it. Just remember nature of the electrolytes also affect the electrode potential. And final one is the, no, not the final one, there are two. Pressure of the gas. If you change the pressure of gas, the reduction potential will be changing, right? So this is applicable for gas electrodes only, right? So let's assume there are hydrogen electrode. So the the equilibrium reaction is 2H plus A equals 2 electrons, equilibrium with H2 gas, right? Let's assume I'm increasing the pressure of H2. So what is the Le Chatelier's principle? If you increase the pressure, system doesn't like it, system tries to decrease it. Therefore, it will favor in the direction where the gas molecules are lesser. This was studied in Le Chatelier's principle, right? When you increase the pressure, system will try to decrease it. To decrease, system will favor where the gas molecules are less, right? So you can see here, the product side, one gas molecule is present. In the reactant side, zero gas molecule is present. So system will favor the backward direction, right? So as a result, electrons will be increased, therefore reduction potential will be decreased, which means it will be becoming more negative, right? So by changing the pressure of the gas, you can change the reduction potential, right? Okay. And the fifth factor is the type of the electrode. If you change the electrode, you can change the reduction potential. Type of electrode. Fifth one, type of electrode. Right. Is the reduction potential of magnesium electrode and calomel electrode same? No, right? So electrode potential changes from electrode to electrode. So by changing the type of the electrode, you can change the reduction potential, right? So those are the factors which affect the electrode potential, right? Okay, so That's it about electrodes. Next we have to talk about electrochemical cells and then electrolytic cells, right? So basics of those two are electrodes, right? So we have discussed about electrodes, how they function, how the voltages are measured, right? What is the limitation in measuring the actual voltage, and the type of electrodes, IUPAC naming, and finally factors affecting factors affecting the electrode potential, right? So six topics mainly we have discussed, right? Right, okay. So I was unable to do the class today, right? So this is a recording is provided. Okay, you all can look at it. Okay. So I hope everything is clear. If you all are having any doubts, you all can WhatsApp me in the group also, right? Okay. So that's it for today, right? Good night. We'll meet you in the next class. Okay.